It's Gordon, aka Eeyore Equus from Reddit again, with another video, this one on polar alignment, in an attempt to demystify polar alignment a little bit. We're going to talk about what polar alignment is, a little bit about the nature of drift alignment in order to achieve a good polar alignment, why we need it, and why it's really, to be perfectly honest, quite a bit simpler than a lot of folks make it out to be. It is really just a couple of circles on top of one another, or at least ideally they're on top of one another, and if you can simply visualize a couple of circles, you can do drift alignment, you can get a good accurate polar alignment with your equatorial mount, and you can track stars as they move across the sky with minimal to no star trailing, even without a guider if you have a high enough quality mount. So let's get started. First thing we're going to discuss is what polar alignment is, or what we mean by the topic, and we're going to use this handy little polar alignment simulator that I wrote. It's not great, but it'll do the job for what we're doing today. And we start here with Earth floating in space. Here's the celestial sphere, if you will. The stars are at least reasonably accurate. They're mapped from an image of the stars across the sky, so they're a few pixels off here and there, but yeah, they'll work for what we're doing here. And we've got on the surface of the Earth in the southeast United States a very poor representation of a telescope on an equatorial mount. It can rotate in RA and declination, as we'll see here. There it is rotating in declination, and if you zoom in far enough, you'll see it rotating in RA as well as the eyepiece there, or the focuser, spins around. So there it is in RA and declination. And we can also move the mount. We can change the mount's elevation up and down, as you'll see here, and we can change the mount's azimuth. We can move the mount right and left as we need to. Okay. For our simulation, we've also got couple of indicators here, one that indicates the axis of the Earth as it moves through the two poles, the axis that the Earth rotates around, and another that indicates which way the mount is the scope is currently pointing. And we'll start there. We'll tilt the Earth back around, and we'll talk about what polar alignment is, why we want to do it. Polar alignment is really just pointing your equatorial mount, or any mount, but for the purposes of this discussion, an equatorial mount, it's pointing your mount at the celestial pole. So what is the celestial pole? Well, the celestial pole is the point around which the Earth rotates. It's really not any more complicated than that. If we, for example, take a look here, there we go, whoops, there we go. We take a look at the axis running through the Earth's north and south pole, the axis the Earth revolves around, and we'll let the Earth spin here just a little bit so you can see how the Earth revolves around that point there. If we let the Earth rotate around that point, that axis will point at a particular spot in space. That is the celestial pole. Up here is the north celestial pole, and down below it, of course, is the south celestial pole right there. We'll deal with the north celestial pole for the purposes of our video today. So we're going to deal with the north celestial pole. And like I said, it's just that point that the stars rotate around. Well, there we go. We can demonstrate this. We'll move our mount. Our mount is currently 36 degrees low, as you can see. So we'll move our mount up, and there it is, tracking up that handy green axis that we've got there, until our mount, and thus our scope, because our scope is currently at zeros, if you will. It's zeroed out. It's aligned with the mount, if you will. And we'll move this up until we're pointed at the north celestial pole, and we'll actually be a few pixels off from the X here. Again, that mapping of the sky, but our numbers are correct here, so we'll get them right here. There we go. And we'll start rotating the Earth, and we'll notice that those stars revolve around the north celestial pole, just like we talked about. Okay? They do this because, go figure, this is the point the Earth is revolving around, so the stars, which are actually fixed in space, appear to be rotating around it, although they actually aren't moving. As a professor in an astronomy class I took recently said, if everything around you appears to be rotating, it's probably you that is rotating. And in fact, we are rotating here on the surface of the Earth. So all of the stars, and this will be true even if we move a little bit away here, and we'll notice even the stars further out will appear to be rotating around that celestial pole. This will be true of every star in the sky. Every star in the sky will appear to be rotating around a fixed point in space known as the celestial pole. All right. Well, our goal then with polar alignment is to align our mount or point our mount directly at that spot. Why do we want to do that? Well, we looked earlier about, in the case of an equatorial mount, its ability to rotate in RA, right ascension, if you will. All right? And we can watch the mount do that as it rotates around that point. It's basically rotating around that beam, and you'll see it's rotating very precisely around the center of that axis there. So if our mount is pointed at exactly the same point in space that the stars rotate around, and then our mount rotates around that point as well, then we can be assured that the mount will rotate at the same or in the same path as the stars it's pointing at. They'll both have the same center point. They'll both be rotating around the same place, that north or south celestial pole. If we can rotate around that same point in space and do so at exactly the same speed and in the same direction, then the stars will effectively remain motionless in the field of view of our telescope and allow us to photograph them. Let's demonstrate that. We're going to go ahead and align our mount precisely here with 0 altitude error and 0 azimuth error. And then we will go ahead and start spinning the planet here. We'll fix on a star, spin the planet, and we'll enable and disable tracking to watch the fact that we can, in fact, track the stars. All right, here we go. Just there we go. Now, next thing we're going to do is we're going to spin around here just a little bit, and then we're going to aim our mount at a star in the southern sky. And notice, by the way, while we're we're aiming our telescope, not our mount. And while we're slewing the telescope here, notice that we're heading south, and here shortly we will cross the equator, which is handily drawn in Space Force in this simulator. And there it is, right there. And notice that as we are heading south, the equator came from our left here in our field of view, so we're going south toward the equator, and now we've crossed it. This lets us know that south is on this side to the left of our field of view for this purpose of this simulator. Now, obviously, there's not a handy equator in the sky when you're actually taking images, so we will discuss here shortly how you might be able to determine where south is in your field of view, because it will vary depending on which way you're approaching from, what sort of telescope you have, whether the optics are flipped, that sort of thing. But for purposes of this simulator, remember that south is here on the left of our field of view, at least currently it is. So let's see here. We're going to change our view so that we know we are in fact pointed vaguely south at least. That's fine. We are correctly aligned with the north celestial pole. So we're going to enable tracking. We're going to start rotating the Earth. Now, notice, the Earth is in fact rotating, but the stars are not moving. The reason they're not moving is by having enabled tracking, we are spinning the telescope in RA, right ascension, at the same speed and in a direction to offset that motion of the Earth. So we're at the same speed, we're rotating around the same point, and we're going in the right direction. Now, stars are simply not moving within our field of view. You'll notice that our field of view has now started trying to stare through the Earth because it is trying to stay pointed at exactly the same star, the same point in space, all the way around, which is fine as long as it's on this side of the Earth where the star is. But right now it's on the back side of the Earth. The scope is being very obstinate and trying to point at the same point in space, and we'll find out that it is in fact succeeding. It just happens to have to be trying to look through the Earth at the moment to do so. Here it comes around. You'll see that its line of sight there is going through the Earth, and it's just about to break, and there we go. Right over the edge there. And our stars have remained exactly motionless right where they were in our field of view. Again, we've been able to do this because our mount is pointed at exactly the same spot in space, the north celestial pole, that these stars appear to be rotating around. As a result, the stars can remain motionless if we offset that motion by revolving around that spot. Okay, so what happens then if our mount is not aligned? Well, we've heard probably discussion of drift alignment. In other words, we try to look at a star, and then we enable tracking, and we see which way the star drifts in our field of view. And if it drifts a certain way, that indicates that our alignment is off in one way or another. We can do that because, as we said, these are basically just two circles overlapping each other. We'll go to another simulator here in a minute and see how that works. But let's first demonstrate If you've done drift alignment or read about it, you've probably heard that if you are in the northern hemisphere, we are, and you are looking at a star in the southern sky, we are, and you observe a southern drift. Remember, that was this direction in our field of view. So if you observe the star drifting to the south, then your mount is too far east. Now that's a whole lot to remember, but let's take it as an article of faith for now. So we're going to adjust our mount too far to the east. We use the WASD keys here, and we're going to adjust our azimuth error about 1.5 degrees or so, too far to the east, give or take a little. Doesn't have to be precise. Now, here's our stars that we're going to watch. We have enabled tracking. We're going to start rotating the Earth very slowly here, and already we can see there go our stars. They are indeed drifting toward the left or toward the south of our field of view. If we speed them up, it becomes quite apparent and dramatic. Now, one of the things you're going to notice is that as we start moving, getting closer and closer around over here to the horizon, this drift isn't so dramatically south and now has an eastern or western component to it. And in fact, as we get to the end of the night, if you will, the stars actually almost start to reverse direction. And what that's telling us quite plainly is that that's why we choose the stars we do to do drift alignment. We choose them in their locations specifically because we can very easily predict which way they will go, and their drift is very dramatic and very distinct. Now, the reality is that you could drift align on any pair of stars or even any single star anywhere in the sky. Yes, even Polaris. It just becomes much more difficult because the drift is much less noticeable and it is much less distinct in direction. So let's go ahead. We'll finish our rotation around here, and we'll get back to where our stars are in the southern sky for us. There we are. And as we start getting more toward the middle of the evening there, you'll notice that our drift now becomes, again, much more distinct, much more noticeable, and much faster. And this is about when we'd actually be doing our alignment, and there they are, quite obviously drifting to the south. All right, well, we'll stop the planet from rotating here. And now we'll go demonstrate the other part of drift alignment. They tell you to pick a star in the east or west. So let's go ahead and, whoops. Not what we wanted to do there. Now we'll go ahead and spin the planet around here and get ourselves reset to where we wanted to be. There we go. Planet's really moving. It's a short day right there. All right. Now, let's see here. Let's move our scope here a little bit to the east. Oops. Getting backwards here. Alright. There we go. And we're going to pick up a star in the eastern sky now. And it can be just roughly any star anywhere in the eastern sky. It really doesn't have to be any particular star. So roughly east will work. Now there we go. Those stars will work just fine. And now we're going to correct our azimuth error in our mount back to 0, and this time we're going to make the mount too high or too low. Again, if you practice drift alignment or read about it, you've probably heard that if you're in the northern hemisphere, a star in the eastern sky will drift south if your mount is too low. Okay, fine. So we're going to move our mount a couple of degrees too low here. Remember, south was over here to our left again. Now we have a mount that is too low. We start rotating the Earth, and sure enough, there go our stars drifting again to the south, just as we said they would. Okay, so we've kind of demonstrated that drift alignment does in fact work, and to be perfectly honest, as we said, you could really pick any star in the sky you wanted to. You know, it doesn't have to be a southern or eastern star or a northern star. It could be a southeastern star if you wanted. You could pick a star over here. And if your mount is misaligned, that star is in fact going to drift. But it's not going to drift in a very noticeable or distinct manner. It's kind of partially to the, is that to the east? Is that to the south? Is that to the north? We don't really know. So let's go take a look at why that is and why we choose the stars we do, and in fact why they drift. We'll go over here to this other, well, not really a simulator, but this other little program we've got here. And we'll look at why stars drift and why they do so in a predictable fashion. This simulator deals with two circles. This circle here is the path that a star would take around a celestial pole. A little yellow dot there is our star. Here's the center point, the celestial pole, and here's the path that star will take. And we can rotate that star around our celestial pole just as it would move through the sky. We also have a field of view circle. This is the path our telescope will take around a particular point. Here's the field of view of our telescope. This point is the center point. That's the point that our RA axis on our mount is aligned with. In other words, this is where the mount is pointed. And just like the star, it will rotate around that particular fixed point in space. If we enable the star and the field of view, we see that right now they are on the same point in space. So if we rotate both of them, let's center our star here, we rotate both of them, with respect to our field of view, the star will stay in exactly the same place. It doesn't go anywhere. It stays right there, centered in the field of view, no matter where we put it, or how far, or how fast we rotate it. Because again, this mount is aligned. In other words, it is pointed at the same point in space that the star is rotating around, the celestial pole. So as they rotate, they do so together and consistently. Alright, so let's misalign our mount. Let's move its position a little bit over here. Now notice that our mount is not quite aligned with the same point in space that the star is. It is not pointed at the celestial pole. Well, let's watch what happens here. We've got a star centered in our field of view. We begin to move, and you'll notice the star moves within the field of view. Specifically, it moves down or this way toward the celestial pole, if you will. And then as we move around a little further, it moves over here to the side. Now it's moving up and away from that pole until right here, and now it's moving back down towards it until we're back centered again. Just like the stars in our field of view in our other simulator did. As one full day progresses, the direction of the movement and the speed of the movement changes depending on where we are in the day, but it is always predictable. Okay? Now, let's take this a little bit more, make this a little bit more realistic, if you will, and let's presume that this yellow dot, the center of our star's movement here, this yellow dot is the southern celestial pole. Okay, so this is a southern star, if you will, a star in our southern sky. Well, now, if that's the case, if we are facing south here, the north is back behind us. All right, so let's enable our field of view here. Here is our mount. It is pointed slightly to the right, or west, because remember, we're looking south, so south is here, west is over here. It is pointed slightly to the west of the southern celestial pole. If that's true, the back of our mount is pointed west of the south pole, then the front or north of our mount must be east of the north celestial pole. Now, remember your drift alignment. Drift alignment says that if we are in the northern hemisphere, we are, because we're aligning with the north celestial pole, and a southern star, this is our southern star, moves south in your field of view, then your mount must be too far east. Well, remember, the back end of our mount is too far west, so the front end of our mount would be too far east, so our star should move south in our field of view, and sure enough, as we start rotating them, the star moves away from the center of the field of view and closer to the south celestial pole. That star is indeed moving south in our field of view. That statement will be true from the moment the star rises over in the eastern hemisphere. It is way up here, and as we move around, it begins coming down closer to the center. Now it's coming down closer to the edge, all the way over to the other horizon, demonstrating that your southern star does not have to be due south of you for drift alignment to work. Why then do we suggest that you choose a southern star, or one that is close to due south of you? Well, quite simply put, notice that the difference in positioning isn't very far over here. This star is right here, about 2/3 of the way up, and for quite a while, it's barely drifting south until about this point right here. Now, once we get about to this point, roughly call it southeast or south-southeast, now the movement of the star toward the south is very dramatic, very quick, and very precise. It is obviously heading south and south only, and then toward the end of the evening, if you will, as it's getting close to this horizon, it's still moving south, but not very far and not very distinctly. Okay? Let's presume here for a minute that we're talking about the altitude of our mount instead of the instead of the azimuth of our mount. Okay? So let's raise our mount, the back end of our mount, too high. Now remember, the back end of our mount is now too high. It's above the pole. So the front end of our mount, the end we're trying to align, is obviously too low. It is below the north celestial pole. And again, in drift alignment, we say if your eastern star, well, remember, we're looking south, so an eastern star would be one over here. So let's move him over here. There we go. And we'll center him roughly there in our field of view. Your eastern star will drift south if your mount is too low. Our mount is too low. We expect the star to drift south. And if you're paying attention, you've been watching how this circle behaves, you can already see what's about to happen. As our eastern star rises, the star moves to the south very distinctly and very clearly within our field of view. Now, could we align on the western star? Absolutely. But if you've read again about drift alignment, you'll notice the directions are reversed. Your western star should move to the north if your mount is too low. And as we observe, here's our western star, and sure enough, it is moving away from the pole or to the north within our field of view. This is how and why drift alignment works. It's just two circles. Our field of view has one circle that rotates around one point. Our star is another circle that rotates around another point. When those points are precisely aligned, the star will remain motionless within our field of view. When they are not, the star will drift, and it will drift in a predictable direction and manner. Could we drift align on any star in the sky? Absolutely we can. We could even drift align on Polaris itself if we wanted to. Not exactly recommended. It would be an incredibly difficult thing to do, but just to prove the point, we will demonstrate that if you are in fact misaligned, Polaris will drift in your field of view. Here we go. We're going to align our mount very precisely. There we go. Very precisely around mount. Here is Polaris right here. We're going to enable tracking. We're going to start rotating the Earth. Okay. Polaris is motionless, as we'd expect it to be on a properly aligned mount. But now we are going to misalign our mount about 1.5 degrees here, or about 3/4 degree or so, and Polaris is in fact drifting just like any other star in the sky would. Now notice, across the entire 24-hour day, Polaris not only never even leaves your field of view with its drift, it barely even leaves this quadrant of your field of view. So the drift is very, very minor, very difficult to determine, and again, very difficult to predict. But it is, at least in theory, possible. So validating the statement that you can drift align on any single star in the sky. So that is drift alignment and polar alignment, what polar alignment means, how and why drift alignment works, and why drift alignment is really nothing more than just two circles in the sky rotating around hopefully the same fixed point in space. Hopefully we've demystified polar alignment and drift alignment a little bit for you, and until next time, thanks for watching.